Moving on to objective 3, we want to solve special systems by graphing. So a system with at least one solution is called a consistent system. So in the case of the problems that we just saw, that had one solution, so it's a consistent system. A system with no solution is called an inconsistent system. So different forms of the same equation, such as x plus y is equal to 2 and 2x plus 2y is equal to 4. These are known as different forms of the same equation, since we see that our second equation there, our 2x plus 2y is equal to 4, is just x plus y is equal to 2, but multiplied by 2. So we see that each term in that equation is just multiplied by 2 to give us this new equation. So we're really dealing with the exact same equation. We've just now scaled it up by 2. So saying that, different forms of the same equation are dependent equations, so anything else is considered an independent equation. They're dependent equations because we see that their lines are actually going to overlap. So they're going to be dependent equations. So in any case, if you don't end up with equations that just have different forms, they're going to be an independent equation. So this is really the only case, or it is the only case where we have a dependent equation. Anything else is an independent equation. So we have a summary of our special cases, and there's 3 cases for our solutions of linear systems with 2 variables. So case one, we have that the graphs intersect at exactly 1 point, which gives the singled ordered pair solution of the system. The system is consistent and the equations are independent. So we see figure 5a and b. So below here we have our case 1 and our graph, which corresponds to figure AB, which just shows our 2 separate lines intersecting at 1 point. The system is consistent because it has one solution, and the equations are independent since they are not the same line. Then for case 2, we say that the graphs are parallel lines. So there's no solution, and the solution set is the empty set. The system is inconsistent, but the equations are independent. The equations are still independent because it's not the same equation of different forms. So they are still going to be independent, but it's inconsistent since there is no solution. And this would be the case in which there was no solution. It would be when your lines are parallel. So our case 2 of when our lines are parallel correspond to our graph B. So we see we have our 2 parallel lines. They'll never intersect, so we have no solution. We see our system is inconsistent because there is no solution, but the equations are still independent. Then lastly, case 3, the graphs are the same line. So this is what we see with our different forms. Even if it's scaled or each term is multiplied by 2, we still see that when we graph them, they are the same line. So this means that there is an infinite number of solutions. If they're just 2 lines overlaid, they have an infinite number of solutions, and the solution set is written in set builder notation as x comma y, where we see some equation, where one of the equations follows the vertical bar symbol. So you could pick any equation in that case. The system is consistent and the equations are dependent. Since we have an infinite number of solutions, our system will be consistent since we have more than one solution, but the equations are entirely dependent. And this corresponds to our figure 5C. So we just see one line drawn here, but this just means that we have 2 lines layered and we have our infinite number of solutions. So our system is consistent, but the equations are dependent. So keeping that in mind for objective 4. We want to identify special systems without graphing. So in the case that you were graphing special systems, these are just the main graphs that you want to look for when determining if something is a special system or not. That's really just what you're looking for. You're looking for parallel lines and lines that overlap each other. But identifying special systems now without graphing is going to be a little different. So example 3, we want to describe each system without graphing and state the number of solutions. So remember what we're looking for. We're looking for parallel lines. And the same equation, but different form. So this is what we're really looking for when we do these problems. So let's start with problem A. So problem A, we have 3x plus 2y is equal to 6, and negative 2y is equal to 3x minus 5. So we're going to go ahead and we're going to rewrite these in our slope-intercept form. So we write part A over here. We want to rewrite in slope-intercept form. So we know equation 1 and equation 2. We write them now side by side so we can solve them. So equation 1, we have 3x plus 2y is equal to 6. And equation 2, we have negative 2y is equal to 3x minus 5. So we're solving for y in this case. So for our first equation, we're going to go ahead and we're going to subtract 3x from both sides. So we get 3x plus 2y minus 3x is equal to 6 minus 3x. This now gives us 2y is equal to negative 3x plus 6. Since we're solving for y, we just want to divide each term now by 2 so we can isolate y. And this is going to give us y is equal to negative 3 halves times x plus 3. So this is our equation 1 in slope-intercept form. Now we want to do the same thing for our second equation. We already have y, our y term, isolated to one side, so now we just want to divide each side by negative 2. So divide by negative 2. Now we get that y is equal to negative 3 halves x plus 5 halves. So when we want to look for parallel lines, we're looking for lines that have the same slope, but not the same y-intercept. So in this case, for equation 1, our y-intercept is going to be 0, 3. And for equation 2, we have that our y-intercept is 0, 5 halves. So our y-intercepts are different, but our slopes are the same. So we can say our slopes are the same. So we have parallel lines. This also means that our system is inconsistent and our equations are independent. So this is one of our special cases that we were dealing with. Since we wanted to describe each system without graphing, we've now described our system and we state the number of solutions. Since we have parallel lines, there is no solution. And we can say that this here will be our final answer. All right, so now for part B. For part B, we want to do the same thing. We still want to rewrite our equations in slope-intercept form. And labeling our equations again, our first equation is 2x minus y is equal to 4. And our second equation there is x equal to 1/2 y plus 2. So once again, we want to rewrite in our slope-intercept form. Starting with equation 1, we want to isolate y, so let's go ahead and subtract 2x from both sides. So now we're going to get negative y is equal to negative 2x plus 4. Since we have negative y, let's go ahead and divide each term by negative 1. And when we do, this is going to give us y is equal to 2x minus 4. Now for our second equation, we still want to isolate y. Y in this case is on our right-hand side. But we can just solve for y, and our last step can be flipping it in the other direction. So let's go ahead and subtract 2 from both sides. So we're going to get x minus 2 is equal to 1/2 times y plus 2 minus 2. So we get x minus 2 is equal to 1/2 y. So we can go ahead and multiply each side by 2 to get 2 times x minus 2 is equal to y, where 2x minus 4 is equal to y, which we can just flip to say y is equal to 2x minus 4. So what we see here is that we have the same equation. And since we have the same equation here, so we have the same equation, so we have one line overlapping the other. Which means that our system is consistent because it has infinitely many solutions, but the equations are dependent. And since they are lines just overlapping each other, we can say that, what did we say in our last one? So we can say that there are infinitely many solutions. So we've described our systems and we said how many solutions there were. Then lastly, we have part C. We have x minus 3y is equal to 5 and 2x plus y is equal to 8. So let's go ahead and solve this linear system as well. So part C, we're going to do the same thing. We still want to rewrite in slope-intercept form. Our top equation here we can just label as 1 and our bottom equation as 2. So our first equation is x minus 3y is equal to 5. And our second equation here is 2x plus y equal to 8. So let's go ahead and write these in our slope-intercept form. In our first equation, we want to isolate y, so we're going to subtract x from both sides. So we get x minus 3y minus x is equal to 5 minus x, which we've subtracted x, so we have now negative 3y is equal to 5 minus x. And now we can divide each side by negative 3. So we get y is equal to, and we can rearrange our x terms. So since we have a negative 1x divided by negative 3, this will give us 1/3 x minus 5/3. So this is our equation for equation 1. And then equation 2, we want to do the same thing. So we'll go ahead and we'll subtract 2x from both sides to get 2x plus y minus 2x is equal to 8 minus 2x. Then all we have left is a positive 1y on our left-hand side, which we say is equal to negative 2x plus 8. So we see here in this problem that we have our slopes, which are different, and our equations, which are also different. So this would be the case where we just had one solution. So we can say we have two different straight lines so our system is consistent and our equations are independent. And since we just have two different straight lines, this means that we only have one solution. So what we'd see here for part C, this would be our typical kind of image that we would have. So, all right. Quite the problem there, example 3. But that would be how we would go ahead and try to identify special systems without graphing. So in order to identify special systems without graphing, really remember what you're looking for is parallel lines and the same equation but in different forms. So these are the things that you're really paying attention to. So all right, that finishes up our video on section 4.1. I will see you again in section 4.2.